All right. Go out there. All right. So let's get back into what we did last time. Just to remind you guys, we made it to this point here. Let's see if I remember. So we made it here. So let's do this. We'll try a problem out. Then I'll let you guys try a problem out. Then I want to say something about my shirt. And then we'll get into section 84. And they actually have the degree version of this on page 561. We try to stay away from degrees, just in general. So let's see. If I had this question, z to the 6 equals, I don't know. What do I pick? Yeah, we could do that. Let's do... well, okay. Let's do one that's got some... We'll do one like this guy. So, does somebody know the real solution to that? 2. Yeah, 6 2's multiplied to 64. So, there's the real solution. Now, there's going to be how many complex solutions? There's got to be 5 complex solutions, right? So you can look at this, of course, as the 6th root of 64, or 64 to the 1/6 power. So there must be 6 answers to that, this expression, to be honest. The one we normally think of is the real answer, 2. What do I have to do first in order to use this formula? What do I have to do first? What do I need to identify in order to be able to use this formula? I need to change my number, 64. I need to change it into polar form. So I need the polar form of the complex number 64. Is everybody cool with the fact that he just called 64 a complex number? Right? Yeah. What did you call 64? All right. So I want to change 64 into polar form. And how do I do that? So the first thing to realize is, what is this in this form? So it's 64 plus 0i. Awesome. You guys still with it? Because I need something that looks and acts like a point in order to change it into polar form. Because polar form eats points up, right? R would be the x and y squared, added, square rooted, so forth. So how do I get... So R, hopefully, does anybody realize what R would be? I like that, but it's wrong. What's x?
64.
Alright, so it's the square root of 64 squared plus 0 squared, so R is 64. If I plotted this point, let me make my scale that. Wouldn't it be here? How long is that? Alright, so R is 64. So you don't have to do work. That's awesome. If it's at a diagonal, shit, I don't know what the distance is, I got to do the work. But if it's on one of the axes, I don't have to do any work. I know exactly how long the thing is. It's whatever the point is. Alright, so be real careful about making assumptions about things. So yeah, R is 64. What else do I need? Theta. Alright, so how do I get theta? Yeah, you do all this crap if you want to, but again, what's theta? 0. Kick ass. Do you guys see that? I mean, I only have to do this, let me say rad just to be specific. I only have to do inverse tangent when I have something that I don't, the angle I can't identify from a quick picture. If it's on an axis, I know the angle, it's easy. All right, how we doing so far? So the inverse tangent thing is still true, I just don't need it. It actually makes things seem harder than it is in some situations. But it still works, it's still true. All right, so what does 64 look like then in polar? Yes, 64.
Cosine 0.
Cosine 0.
Sine 0.
Plus I sine 0. So it's got a very boring looking, and of course it does, because it's very simple. It's just 64. Alright, so that's all this work here. So in this case, what's n going to be for my problem? What's n?
6.
N is 6 because I want the 6th root. So now I just start plugging and checking. So I get r is 64 to the 1/6. We know what that is. Cosine of... Good. 0. So I get 2 pi k over n, which is 6, plus I sine 2 pi k over 6. Stay with me now. And this, of course, is just 2, like we said earlier. That's 2. I like it. So let's see what this is. Let's call this, what you got, Jeff? So what does k range from to? 0 up to 5, right? N minus 1. And that gives me my 6 answers that I expect, right? 0, 1, 2, 3, 4, 5. That's 6 answers. So if k equals 0, this is the boring answer. And this relates to, k equals 0 relates to, again, here's 64. So the 6th root of 64, one answer is going to be 2. And sure enough, when I plug k equals 0, and what do I get? I get cosine of 0. Is that cool? What's cosine of 0? 1. And what's sine of 0? 0. So I get 2 times 1. I get 2. So k equals 0 picks up the real answer, right? K equals 0 picks up the 6th root of 64. What we normally think of when we say that is the real answer. What we don't realize is there's 5 other answers we never get until now. Okay. So what if, so you guys keep going. K equals 1, k equals 2. You shouldn't have to plug anything in your calculator, by the way. Just make sure everyone's on the right track. What is the cosine of pi over 3? 1/2. So twice 1/2 is 1 plus I. What's sine of pi over 3? Right 3 over 2 times 2? Right 3. So what do you get here? Cosine of 2 pi over 3? Yeah, okay, good. So the cosine of 2 pi over 3 would be negative 1/2 times 2, so negative 1. Yeah, plus I by 3. And what do you get here?
Negative 2.
Oh, why did I put a 3 there? You do it, Jeff. So there's negative 2. Cool. And then okay, 6 negative 2s would make 64, because all the negatives would cancel. So that makes sense. K equals 4. So now you'll be down in the third quadrant. I like it. So now 2, 4, 6, 8. So now we're at 4 pi over 3. Yeah, good. So this will be, everything's negative now. So negative 1 minus I rad 3. For k equals 5, now I'm at 2 cosine of, yeah, good, 5 pi over 3. And we get, and now this is positive, good. We get 1/2 times 2 is 1 minus I root 3. Cool. So 1, 2, 3, 4, 5, 6. I like it. Now, what's almost kind of too obvious to be excited about is the fact that all these answers are exactly how far apart if you plotted each one of them. So here's one answer is 2. If I plot the point 1 rad 3, so I go 1 rad 3, how far is that? What angle is this?
60.
Yeah, because how far apart are all these things? 2 pi over 6, pi over 3. I like it. So that's pi over 3 away. And so if I cut 2 pi in sections of pi over 3, how many of those will I get? 6. Do the word 6. 1, 2, 3, 4, 5, 6. Right? Because there's actually 6 answers of it, because we've got to include 0. What will 0 do? So the funny thing is, you could get one answer. You could get one answer, and then just rotate from there, rotate from there, rotate from there. So for example, if I'm at pi over 3, I know what x and y are on the unit circle. Then I just multiply each of those by 2. Then I just go by another pi over 3. Now I'm at 2 pi over 3. I know what x and y are, multiply by 2 on the unit circle. I actually don't even have to set up the equation. So we took something that used to be basically impossible, or very difficult to do at least, is to solve that by hand, right, and get all the answers. We took something like that, we made it almost too simple, where you really just need one answer and then you just keep rotating by the same angle. I don't know if you guys are with me or not. And if you don't quite get that, you can always just do exactly what we did here. Bam! Just realize, and I love the book does give you a few examples that shows you that they're equally spaced.
Always.
Yeah, they have to be. Exactly. They have to be equally spaced, yes.
What determines what k is? So like if n would be 8, for example, would k be 0 to 7?
Beautiful. You figured. Yeah. And that's just, and I want you to realize, so remember, when we had 3 theta inside of cosine or something in an equation, we solved it, and then we divide by 3 at the end. It tripled the number of answers we normally had, right? Because once you get to k equals, what happens here if I try k equals 6? What happens? I'm back to 2 pi. Now I'm starting to repeat myself. So that's why we stopped 1 before that. So whatever n is, k is going to stop 1 before that, so it doesn't start to repeat itself. You're like, I already said 2. Stop it. So we only want to list the ones that are unique. Cool. I like it. Very good, very good. So, you guys try this one. Let's see. Jeff. Adam, I'm going to give you something that's not too freaky.
42.
Sounds awful. I don't like that.
16.
Well, I mean, 16 still is interesting, but it's not. Well, let's do 16, sure. Do it this way. This way. Otherwise, what's the point? Give me something that won't help you learn this stuff at all. Please, Mr. Waller. The only problem with this example is it's like the 64 one where the angle we're working with is 0 again, right? So it's not always going to be true. So I think we'll do one more quick one after this, just to show you what if it's not true, because this kind of makes it a little easier to look at. In fact, right off the bat, what can I do here? Yeah. Bam. So if k equals, and of course, what's 16 to the 1/4? 2. Yay. So if k is 0, yeah, I'll get 2. If k is 1, I'll get cosine of pi over 2, 0. And sine of pi over 2 is 1, so I get 2i. If k equals 2, because now I'll get cosine of pi plus I sine pi, so cosine of pi is -1, so I get -2. K equals 3, beautiful, because now it'll be 3 pi over 2. Cosine of that 0, but sine of that is -1, so I get -2i. Sweet. And of course, I don't know if you guys remember, but we know that already. How do you factor that? How do you factor that? Z4 minus 16?
Z squared plus 4.
Z squared minus 4, Z squared plus 4, and how do you factor both of those? So yeah, this one's Z plus 2, Z minus 2, so that corresponds to 2 and -2. This one is Z plus 2i, Z minus 2i, kick ass. Alright. Sweet. Alright. So let's do one more where it's not an angle of 0. Let's see. So now I want the cube root basically of 1 minus I. So how do I convert that into polar form? Yeah, R is square root of 1 squared plus -1 squared, square root of 2. And then what's theta? What quadrant am I in? It's always a good idea to graph the thing I'm working with. First is the grounding. What quadrant am I in? Fourth, because you go 1 over and 1 down, right? 1 on the real, and then down 1 on the imaginary. So what angle am I at then? Pi over 4, sweet. And be a little more specific. Negative pi over 4, yeah. Because if I use a reference angle, I'm going to get the wrong roots. I'm going to get the roots for 1 plus I, because that would be the pi over 4 angle would be up here, right? That's the wrong point. It's the wrong complex number. So you can use negative pi over 4. You could have used what instead? 7 pi over 4. But I like negative pi over 4. Let's use that. Yes, sir.
How do you know it's pi over 4 just from the...
Oh, so the fact that they're both equal. It's got to be 45 degrees, yeah. Or you could do inverse tangent of -1 over 1, and tangent's -1 at a 45 degree reference angle. Sweet. I like it. But you see how very often we don't have to use that? It's just I can, if I plot the point, I can tell what the angle is going to be. Okay, good, good. So now I can attack this. So 1 minus I to the 1/3 will be R to the 1/3. Ooh, that's good already. Yeah. Times cosine of negative pi over 4, good. Plus 2 pi k over, yeah, n is 3. Plus I sine of the same business. Coolness. I like it. Real quick, rad 2 to the 1/3. Rad 2 is 2 to the 1/2 to the 1/3 is 2 to the 1/6. So it's just easier to write that. So let me just write that. Yay. Cut it in half, cut it in thirds, you cut it in sixths. Yay. I'll let you guys ponder that. And then the rest of it, blah, blah, blah. So what if k is 0? Do we want to, let's maybe, can we simplify this just a little bit? Do you want to? Or do you want to just attack it each time? Either way, I don't care. Do you understand the question? If we simplify this, I'd have to multiply by 4. I get like 8 pi k minus pi over 12 or something. I mean, it's not really overly simplified. All right. So let's see. If I make k 0, what do I get?
Negative 3 pi.
I get 2 to the 1/6 times cosine of
Negative 3 pi over 4.
negative pi over 12. Right? Because it'll be negative pi over 4 divided by 3. So now it's divided by 12 total. Right? And that, if I wanted an exact answer, I could use
Half angle.
half angle. I'm not going to make you do that. But, you know, if I wanted an exact answer, I could do that. We'll take decimal approximations here. Why not? Plus I sine of the same thing. So somebody help me out. What's 2 to the 1/6 times cosine and negative pi over 12? Make sure you're in radians. There's only 3 answers here, right? 1.08? 4? All right. And then what's 2 to the 1/6 times sine of negative pi over 12? So it should come out negative. 0.291, roughly. So it's approximately this. Cool. I like it. How are we doing so far? I do not expect you to give me, let me say this again. You can use decimal answers when the angle that's left inside is not an angle that you know. If this was pi over 6, I better not see any weird decimal shit. I better see some radicals and some whatever. Does that make sense? Pi over 12 is not an angle I know. So I can just go ahead and use the decimal approximation. If I'm in the real world and I need a real, if I need the exact answer, you could use half angle like we said. What if k is 1? I'll get 2 to the 1/6 times what? So maybe this form does have a little bit of better. If k is 1, yeah, I get 7 pi over 12. So it'll be cosine 7 pi over 12 plus I sine 7 pi over 12. What quadrant is that in?
Third? No, second.
Second.
Yeah.
Because it's 1/12 pi over 6 pi over 12, which would have been pi over 2. So it is one little tick mark into the second quadrant. I like it. Kick ass. Do you have to know that? Not really. It's good to know what to expect. Yeah, exactly. So it's all the over 12 stuff. It's got sort of like the same reference angle in a way. So it just becomes what now?
Negative
0.291i plus. And then the final one here, right? Because I know I don't have to go up to 2 because n is 3. 0, 1, 2. So then I'll get 2 to the 1/6. If k is 3, I'll get 24 pi. I get 23 pi over 12. Is that right?
So the
K is 2. Oh, why did I make it 3? Jeff, come on. Wake up. If k is 2, I'll get 16 pi minus pi is 15 pi over 12, which is...
5 pi over 3.
Yeah, so I get 15 pi over 12, which is 5 pi over 4. Sweet. Which is actually something that you... No! I like the way you said that. Yeah, we know it.
I didn't say it like that.
I understand. What kind of throws us off is this 2 to the 1/6 crap, right? But what I want you to, well, let's see. Screw it. Cosine of 5 pi over 4 has a rad 2 in it, right? What would it be exactly? Do one more time, sorry.
It's a negative square root of 2 over 2.
Yes, negative rad 2 over 2. So it'd be 2 to the 1/6 times rad. It's all negative. And you can get a decimal approximation for that. Right, because 2 to the 1/6 is gross. Doesn't really help me out. And the sign is going to be also negative. And it's going to be the same thing. Minus 2 to the 1/6 rad 2 over 2, whatever number that is. So I had an answer at negative pi over 12, had another answer at 7 pi over 12, and then I had an answer at the pi over 4 reference there. You see, that's a nice tilted p sign. It's they're all equidistant from each other. Okay. Yes, sir.
I guess for k equals 1, you put the I in constant.
I put what now?
The I should be negative 0.291.
Yeah. Oh, yeah. Thank you. Why did I do that? Sweet. This is an I. Cool. Yes, sir.
So, because we know that it's rad 2 over 2, would we not approximate that in a calculator and write
Yes,
it?
totally. Get the decimal for it out of your calculator. I know you guys could do that. So whatever that is a decimal. Cool. Do that. All right. Just want to show you an example where it's not necessarily pretty, because it's not. It wasn't a nice one that was on an axis. It was in between axes. Yeah.
This is not something we can plug into our calculator straight away. There's like the handwork we have to do first, correct?
Yeah. And right here, you do the handwork just to figure out where the angle is, and then you can immediately plug it in the calculator. Yeah. Cool. If it's an angle you know, I do sort of want to see that, but then this I would immediately make it to a decimal anyway, because it's first. Cool. I like it. All right. So I want to say one little thing about my shirt. Yeah, kind of like that. Teacher's always talking about shirt.
Oh, can I ask another question?
Yeah,
You
sure.
got 0 as a number. Like, it's z3 equals 1 minus I. Technically 0, 1, 2, and 3 are 3 numbers. Aren't there supposed to only be like 2?
No. There's got to be 3 answers.
There has to be 3, but isn't 0 counting as 1?
Sure. So there's 1, 2, 3.
Oh, okay. I thought you were also including the number 3, but I see that.
Oh yeah. So we stop. K stops at n minus 1.
Right.
And that's y. That's another way to look at y. So real quick, you have this famous formula, Euler's identity. And actually there's a part on my shirt that we know. It says cosine of pi plus I sine pi. So somehow, what my calc students wrote, we're actually going to do today in my calculus class, my calc 2, we're going to prove this. And that is nothing that is at all obvious. This is e to the I theta equals that. That is so desperately not obvious. In fact, it's so not obvious that you couldn't even imagine that that might be true until you do weird stuff with cosine and sine. Namely, what we did Tuesday in there was we came up with an infinite summation of functions that represented cosine. That's enough of that, sir. So until you get to the point where you even think about doing that and why would that even be a good thing to do? Once you do it, you go, wait a minute. If I add these together, I sort of get what E is. Infinite representation. Holy shit, so then you end up here. And if I plug a pi in, what do I get? E to the I pi would be R times cosine pi plus I sine pi. And cosine pi is? -1, and sine pi is? And this is on the unit circle, let's say, bam, bam. So this would be e to the I pi equals -1. Therefore, e to the I pi plus 1 is 0. Isn't that crazy? And the r thing, I'm sorry about the r thing, I forgot. E to the I theta is on the unit circle, so then you multiply by r to be whatever. Right, so the R is 1 if it's just e to the I theta. Alright, now, what of that do you have to know? None. I've worn the shirt before, I just want to let you know that we have 1/2 of it. The other half is Calculus 2 level. Yeah. Cool. So there's not a damn reason you should know that at all. It's just interesting mathematical fact. So the only other thing I want to talk about today, we're going to finish out, or at least get into 8.4 a little bit. And 8.4 deals with things called parametric. Get out of there. Equations. And so I have a really strange example that I just came up with as I was standing up here. And it might be the cold method I'm on, but we'll see. It's getting cold, it sucks. Ouija boards.
What?
Ouija boards? I'm not going to bring one. I'm not going to do it. But if you imagine the Ouija board, it's a plane, basically, right? In fact, if I wanted to, I can draw an imaginary whatever, and here's yes, and here's no, and here's all the A, B, C crap, right? All right. The only reason I know at all what this looks like is because I've seen that one paranormal activity movie where they had a Ouija board. Bless you, Edward.
Thank you.
When we graph things, and somehow I'm going to connect this to precalculus mathematics, which I like. When we graph things, we normally put values for x and then figure out what y is, right? So if I had to graph the function y equals cosine x over 1 minus sine x, I said graph that. One way you could do that is to make values for x and then see what happens to y. You with me? Let me say that again. I would put values in for x, and then, so for example, I put 5 or 4 in for x and see what happens for y. Is that cool? And then we plot the points. That's not the only way to construct, to have something move or to construct an image. That's not the only way to do it. X controls y in this viewpoint. Does that make sense? So what's really cool here is x and y are both being controlled by some third thing, namely the resultant force of everybody pushing on the damn little whatever you call it. Right? I don't know why I made that sound, but it did. Right. You guys still with me a little bit? So if this person pushes a little harder, then it's going to change. So if somebody's got the little, I don't even remember what it looks like.
It's like a teardrop.
A teardrop?
Yeah. Like a
I've never been to prison. I can't do that. Screw it. It's got a little pointy dude in there. Right. So if somebody's holding it exactly perpendicular, right? So somebody's got it here and somebody else has got it there. If he pushes harder, it's going to move more in the X direction. And if he's pushing it just a little bit, the resultant movement is going to be like that. Are you kind of with me? Now, this guy suddenly pushes harder. The resultant movement is going to be more that way. But the path it takes, that image that results is controlled by a third background variable. That variable being how hard is each person pushing on the damn thing.
Or how hard the ghost is pushing.
Exactly. Which hopefully normally is a ghost of a person, so it's still technically right. Unless you're talking to the ghost of Mr. Ed the horse. I don't know. Were you treated badly? Yes.
Ghost of Bambi's mom.
They basically say things.
Oh man, cold medicine is so awesome.
Maybe the ghost of Bambi's mom.
Who?
Bambi's mom.
Aww. Maybe so. But you better cry for me. Alright. I've never tried that example before, but does that make sense? The idea that is a point in space that is on this plane, right? We're still in 2D, thankfully. You can do all this in 3D. We're going to stick with 2D. So that is a point. X did not determine Y. Both X and Y were determined by some third thing that we call T. That's the behind the scenes, and it's what's called a parameter. This is why these are called parametric equations. Great. So x and y are my variables. They are controlled by this variable, which we normally call the parameter of the problem. So, what you get, yes?
Just a sort of off topic. Since there is such thing as parametric equation, is there such thing as diametric equation?
Oh, so I mean, are you talking about? You could have a third, a fourth. Believe it or not, T is the main dude, but then we can have S, and then it goes to like QRP and stuff, weirdness. Is that what you're trying to ask?
No.
No.
It's fine.
All right. But you can have more than one background force, and that's normally if you're in some higher dimension. Let's stick with 2. Okay, so for example, what the hell would this look like? It would be xt equals t plus 1, yt equals t squared, sure. So one thing we can do is plot this, but then when we plot this, what happens is my normal xy has to have a t component now, right? So always, if you're given a parametric equation, this is a single parametric equation. If you're given a parametric equation, then they have to tell you some kind of a range on t. They have to tell you what is t doing. So let's say t goes from -1. Let's make it -2 to 1. Sure. Just try to make a table of values here and try to plot this thing and see what it looks like. Okay. So let's start with just -2, -1, 0, 1. That sounds good. That's what t does. So t is the background force. T is the resultant force of all the people holding that, or whatever spiritual elements you have that want to play with you on the Ouija board, right? And then they set it on fire and shit, weird things happen. The kid wears the freaking blanket and stuff happens. So what's x if t is -2?
-1.
That's great. And what's y?
4.
What's x if t is -1?
0.
0. What's y?
1.
1.
0.
0.
2.
2.
1.
1. All right. Then you sort of block this out and you plot those. Let's plot those. So -1, 4, 0, 1, 1, 0, 2, 1. So that's what we get. Of course, what does that look like it wants to be if I increase that? Parabola. Yeah. So this is a semi-boring example. It was just to get you into the feel of the mechanics of how to do these kind of problems. You do this all the time. Thankfully, they're going to give us more interesting equations that are going to come up with some really funkadelic pictures and stuff. That's not extra funkadelic, but it's pretty decently funkadelic compared to what we normally grasp. Right? Now, can somebody help me? Can you eliminate t? Kill t. So I know that x is t plus 1 and y is t squared. Can you tell me how x and y are directly related then? Can you eliminate t?
No.
T equals 1 minus x.
You do. All right. Well, all right. I'm sort of with you. So I know that t is x minus 1. Because if I have a variable that I don't want, what do I do with it? I solve for 1 and then I plug it in. So I kill it.
So why?
So what's y? Y equals minus 1 squared, which would be a parabola that shifts over 1. There you go. Right? So again, this is a very basic example. There's no reason I had to put this into parametric equations. Didn't make anything easier. But this is just a feel for how this works. There are instances, for example, like some of the stuff on this handout, where you desperately want to work with a parametric version. Take a minute here real quick and try to Do what we just did for the first problem. Should come out more interesting.
In your example, x is equal to t equals 2 plus 1. When we were figuring out the chart, when you're plugging in negative t equal to 2 for the solving, that's where you got negative 1 in.
Totally. You gotta plug the t into each one.
Okay.
Yeah, so t truly is like a variable for each variable. That's probably given a different name. Call it the parameter behind those variables. So we don't have like the variable for the variable of the variable. Shit, no.
Do we graph these in forward as well as rectangular?
Well, this is.
No, yeah. Let's not bring polar into this. Do you understand? You could talk about parametric style polar equations, but we're not going to. So our parametric equations will utilize trigonometric functions, but that doesn't mean that you have to worry about polar stuff. Does that make sense? So you totally could have like a polar graph and plot a parametric thing on it. We're not going to. That's a little bit above us.
All right.
Is that?
I think it's a bird.
Okay.
Okay.
Are we using that scale?
Yeah, it says t goes from -4 to 4. You see that?
Yeah. Cool. I get it.
Otherwise, you might drive yourself
I
insane.
thought we were gonna. I kind of ignored that. I was just gonna put my own numbers in.
I like this. I don't like your question, Jeff. I think you meant to ask this.
You're right.
I've had students do that on tests. I don't like that one. I can answer this one. Good job. The parallel universe, you get some points. So let me catch up, you guys. Sometimes it's easier to kind of do each one, so I'm just going to do all the ones for this. So when you plug this in, what you end up doing is cutting in half multiplied by pi. So sine and -2 pi is 0. Sine and -3 pi over 2. Yeah, negative 3 pi 2 would be pi over 2, so 4 times 1, 4. I like it. Is everybody cool? Sine of negative pi, 0. Sine and negative pi over 2. Negative 1 times 4, I like it. I think you guys see the pattern now. Maybe, right? 0. 4. 0. Negative 4. 0. Alright, sweet. Alright, cool. Now attack the other equation. When you plug a negative 4 in here, you get 16. Half of that is 8 minus 4 is 4. Plug in a negative 3. 0.5, right? Is everybody with me? Plug in a negative 2. Half of 4 is 2 minus 4 is negative 2. So plug in a negative 1. 1/2 minus 4. That's crazy. Plug in a 0. That's hard. Plug in a 1. That's going to start to repeat, right? You guys see that? Negative 2.5. Negative 2. 0.5. 4. Okay. I like it. So you don't even have any clue as you do this what it's going to look like. You're just filling in this point. Now you look at these each as their own points, right? Let me make sure we're looking at that right. So I'm going to plot this. I want to go out to 4 in all directions, basically. So I got 0, 4, 4.5. You can do it, Jeff. 4.5. 0, negative 2. So 0, negative 2. And be very careful. It's a lot like the polar graphs. When you go to connect these, you have to connect the dots in the order that they were created. Right? So you sort of can kind of keep going there. Where am I at? Negative 4, negative 3.5. So negative 4, negative 3.5 is right there. 0, negative 4. 4, negative 3.5. So get the mirror image over there. 0, negative 2 again. So, negative 4. You gotta love drugs. Let's see, negative 4. Legal drugs. 0 to 4. I am being taped. So what is that? That's a fish going up, right? Or that's a whatever you want to call it. Kind of nifty. And actually, if you expanded the range of t, it would keep going up and get fatter as you went. See how skinny this poor little dude is, and then this guy gets fatter, and then this guy gets fatter. It's kind of neat. It really, really is. It's not just me. I keep telling myself that. So that's kind of cool. That's really cool. I'll show you this. The last thing we'll do, and then we'll finish out that thing next time. If you go to your calculator and you change the mode, remember how we changed the mode to polar? Well, there's one in there called PAR. So hit the mode button. Right beneath radian degree, you got func. You got the func there. You got PAR and polar. So go to PAR for parametric. See if this guy turns on by the time I finish talking about him. Anybody playing along with me? You guys with me if you're playing along? Hit mode. Go from polar to parametric, PAR. Then when you hit y equals, you have xt and yt options. There it is. Cool. So then you can plug in there. Let's see if I remember what it was. Sine. What was it? 4 sine.
Pi t over 2.
You can do it, Jeff. 4 sine. Pi t over 2, right?
Yeah.
Yeah, because it's strong at the end. And then 1/2 t squared, right? Minus 4. Right? Minus 4. And then change your window to match what I want. T I said was from negative 4 to 4. You guys with me so far still? You guys kind of with me?
We just plugged in this equation.
Just plug in those two equations to make one complete picture. Go to Window and make your T do the right thing. And then if you graph it, you get the giant goldfish coming to the surface of the ocean to terrorize the citizens. Since the shark's got a chance, it's my turn. Sure, Jeff, whatever you say. And again, if you're not careful with the scale, you'll get some really. Oh, that's not too bad. Oh, poor little fish that doesn't sound good for the fish. If you make it too good, it'll take forever. Alright. So that's plenty. We'll finish out the handout next time. That's enough for today. I gotta go re-up my beds.
So is the rest of this worksheet part of 8.4 as well?
Yes. Yep. The whole worksheet's from 8.4.